This section title tells us the quiz focuses on how multicollinearity, high correlation between predictor variables, affects Kernelridge regression, a specific type of regression analysis. I'm going to learn how this machine learning technique handles situations where my input data has redundant information. I'm presented with a problem. I'm using Kernelridge from scikit-learn, a popular Python machine learning library, and my data has multicollinearity. I need to figure out how that affects my model's performance. This sets the context. I'm using Kernelridge in a regression task, predicting a continuous value, and facing the challenge of multicollinearity in the features. This option suggests that the uncertainty, variance, in my predictions will increase due to multicollinearity. I need to determine if this is true for Kernelridge. This option suggests that my model will learn the training data too well and perform poorly on new, unseen data. I'll need to consider if Kernelridge is susceptible to this issue. This option focuses on the model's coefficients, numbers representing the importance of each feature. It implies that these coefficients might be unreliable if I'm using a linear kernel, a simple kernel type. I should check how Kernelridge handles coefficient instability. R² measures how well the model fits the data, 0 to 1, higher is better. This option claims that multicollinearity will dramatically reduce this score. I need to determine if this is always the case. This section provides a brief overview. Multicollinearity is when predictor variables are strongly correlated. I need to understand how Kernelridge deals with it compared to other methods like ordinary least squares, OLS, regression. The question is testing my knowledge of how multicollinearity affects the specific machine learning algorithm, Kernelridge regression. It's crucial to understand how regularization in Kernelridge helps handle this situation. These are the multiple choice answers provided for the question about how multicollinearity affects a Kernelridge regression model. I'm evaluating each option to see which are true statements about the impact of multicollinearity. This section details how a Kernelridge regression model handles data. Remember, Kernelridge KRR, is a type of regression that uses kernel functions and adds a penalty, regularization, to prevent overfitting. I'll focus on how the regularization affects the impact of multicollinearity. It's a clever way to improve the model's stability. This phrase reminds me that the data used in the problem is assumed to have multicollinearity. Multicollinearity means there's a high correlation between the independent variables. I need to think about how this impacts the Kernelridge regression model, given the regularization aspect. This is a key part of the analysis. This sets up the core problem. How does multicollinearity, high correlation between predictor variables, affect the performance of a Kernelridge regression model that uses scikit-learn? I'm going to analyze each multiple choice answer carefully. This section introduces the context of using scikit-learn-skernelridge for regression with multicollinearity. It's important to remember what kernelridge is and how it works. It uses a kernel function, a way to map data, and includes regularization, a penalty to reduce complexity of model. I am looking at how the problem of multicollinearity affects this type of model. I see Kernelridge regression as a fancy regression technique that uses something called a kernel function to cleverly transform your data into a higher dimensional space. This transformation often makes it easier to find a good fit, even if the data is initially complex. Think of it like looking at a tangled mess of yarn from far away versus up close. The kernel function helps you see the structure more clearly from a new perspective. The kernel function is the heart of Kernelridge regression. It's a mathematical function that calculates the similarity between different data points in your dataset. This similarity calculation is what helps the model decide how to best fit a curve through your data. I would think of this kernel like a magical lens that lets you see the hidden relationships between data points. Regularization, specifically ridge regression in this case, is a way to prevent overfitting. Imagine fitting a curve to just a few points. It might look great for those points but might be terrible for new, unseen data. Regularization adds a penalty to the model's complexity, gently pulling back any curves that are too wild and keeping things closer to a simpler, more general solution. It's like adding a stability constraint. It prevents the model from becoming too specific to your training data. Multicollinearity means that you have multiple features in your data that are highly correlated with each other. It's like trying to determine the effects of multiple ingredients in a cake, when two ingredients are virtually the same. This correlation makes it hard to pinpoint the individual effect of each feature, leading to unreliable estimates and increased variance in your model's predictions. I'll explain how Kernel-Ridge regression handles multicollinearity. Remember, multicollinearity means features in your data are highly correlated. This is a problem because it makes it hard to isolate each feature's individual effect. Kernel-Ridge regression uses a special trick, a kernel function, to handle this. It cleverly transforms your data into a higher dimensional space where the features might be less correlated. It also uses regularization, like ridge regression, which helps stabilize the model by preventing it from overreacting to noisy or highly correlated data. We're using scikit-learn's Kernel-Ridge for regression, and our data has a lot of multicollinearity. The quiz asks, how does this affect the model's performance and predictions? Let's talk about how Kernel-Ridge regression lessens the harmful effects of multicollinearity. The regularization in Kernel-Ridge regression is key. It's like adding a penalty for large coefficients, making the model less sensitive to the noise caused by highly correlated features. The result? A more stable and less variable model despite the multicollinearity. If I use a linear kernel, Kernelridge becomes similar to ridge regression. Multicollinearity can still make it hard to get precise estimates for the coefficients, those values that tell me how much each feature impacts the outcome. However, the regularization helps. Coefficients won't get wildly large or small, keeping things more stable than in plain linear regression. This is false. R-squared measures how well the model fits the data. Kernel-Ridge balances good fit and stability, thanks to regularization. A slight decrease in R-squared might happen, but it's not a guaranteed massive drop. That's because the model is not just trying to maximize R-squared, it's minimizing a combined measure of error and coefficient size. This is a type of regression that uses a kernel function. A kernel function helps to map the data into a higher dimensional space implicitly, where relationships might be easier to find. This is a technique to add a penalty to the size of the model coefficients. It helps to prevent overfitting and creates more stable models, especially when dealing with multicollinearity. Overfitting means the model learns the training data too well and performs poorly on new data. While extreme multicollinearity could lead to some overfitting, regularization in Kernel-Ridge generally reduces this risk. Multicollinearity usually increases the variability of predictions, they fluctuate more. Kernel-Ridge regression's regularization lessens this, but it doesn't eliminate it entirely. The variance will likely be higher than in a case without multicollinearity, but it won't be drastically inflated. I see Kernel-Ridge regression, KRR, as a supercharged regression technique. It uses a clever trick called a kernel function to map your data into a higher dimensional space, where it might become easier to separate different groups. More importantly, it uses regularization, a way of smoothing out the model and preventing wild swings in its predictions. It does this by adding a penalty for large model coefficients, so it reduces overfitting and handles multicollinearity much better than simple linear regression. Think of it as adding a safety net to prevent extreme results. Pretty neat, huh? This is where the magic happens. Multicollinearity, remember, is when your input features are highly correlated. This makes it hard to know what's truly influencing the output. But KRR's regularization acts like a stabilizer. It prevents the model from getting too focused on any single feature, even if it's strongly correlated with others. The penalty term in the KRR loss function prevents coefficients from getting too big, dampening the effect of multicollinearity and keeping the model more stable. It's like having a wise judge balancing the influence of different witnesses. No single witness has too much sway. Okay, let's break down this question about how multicollinearity affects KRR. We are looking at how this strong correlation between features affects different aspects of a model created using Kernel-Ridge regression. I'm investigating how multicollinearity, highly correlated predictor variables, affects the performance and stability of a Kernel-Ridge regression model, specifically looking at the variance of predictions, risk of overfitting, stability of coefficient estimates, and impact on R-squared. While multicollinearity could theoretically cause some overfitting in extreme cases, It's far less likely with KRR thanks to regularization. Regularization keeps the model's coefficients from becoming too large, thereby reducing the risk of overfitting the training data. Regularization is your friend here. While multicollinearity does generally increase the variance of predictions in regression models, KRR's regularization lessens this effect. The variance might still be somewhat higher than with uncorrelated predictors, but it won't be significantly inflated like it would be in plain old linear regression. Regularization tames the wildness. If you use a linear kernel with KRR, which is essentially ridge regression, multicollinearity will still affect the stability of your coefficients. You might still have trouble interpreting them perfectly, because similar predictors muddle their individual impacts. However, the regularization keeps the estimates more stable than they would be without it. It prevents the coefficients from becoming wildly different based on small changes in the data. This is false. Multicollinearity doesn't automatically lead to a major drop in R² with KRR. Remember, KRR aims to balance a good fit, high R², with stable, reliable coefficients. A small decrease in R² is acceptable if it leads to more reliable estimates and lower variance. I use Kernelridge regression, a type of regression that uses a kernel function and regularization, specifically ridge regression, to make predictions. The kernel function maps data points into a higher dimensional space to potentially find better separation, and the ridge regression part adds a penalty to overly large coefficients to prevent overfitting. This regularization is key to how Kernelridge regression deals with multicollinearity. Multicollinearity means that some of my predictor variables are highly correlated with each other. Imagine two features which are almost identical in their information about the outcome. That's multicollinearity. This creates problems for standard regression models because it makes it hard to isolate the individual effects of each feature. The regularization in Kernelridge regression helps prevent two main issues caused by multicollinearity. First, it reduces the variance inflation, meaning that my predictions are less sensitive to small changes in my data. Second, it helps reduce overfitting, meaning that my model is less likely to fit the training data too closely and perform poorly on new, unseen data. The regularization term acts as a stabilizing force. This is the core question of the quiz. I'm using scikit-learn's Kernelridge, which is a specific algorithm for Kernelridge regression to model data with multicollinearity. The quiz tests my understanding of how multicollinearity affects the results and the interpretation. While multicollinearity can increase the variance of predictions, the regularization in Kernelridge regression lessens this effect. So, it won't be significantly inflated. Think of it like this. Regularization adds a restraint, keeping the impact of multicollinearity in check. Overfitting is possible, but less likely because of the regularization. Regularization is like adding a penalty that prevents the model from becoming too focused on the nuances of the training data. It encourages a more generalized, stable model. With a linear kernel, which is essentially ridge regression, multicollinearity makes it harder to accurately determine the impact of each feature. However, even then, the regularization makes the coefficient estimates more stable than they would be without it. It's like adding a safety net to prevent my model from becoming too wild with the high correlations. The R² score might slightly decrease, but not substantially. Kernelridge regression aims for a balance between good fit, high R², and stable coefficients. A small decrease in R² is a trade-off for better stability in the presence of multicollinearity.